Hello, and welcome to our next slidecast for Astronomy 322. We're going to be leaving coordinate systems behind now and moving into talking about the physics of light. So some of you may have seen parts of this before, others may be seeing it for the first time, or at least seeing it for the first time in the context of astronomy, but it's really useful and important to dig into exactly how we understand light, the basic properties of light, and things like how to build a spectrum and then use spectra in astronomy, because in astronomy, light is all we have. Unless you are someone studying asteroids, in which case your data occasionally comes to you as a meteorite, which you'll hear about a bit in 321, or unless you're in this pretty new field of gravitational waves, which we will hopefully get the chance to talk about a bit in this class. Light is your data. You don't ever get to hold or tweak or poke at the things that you're studying. So it's really useful to understand exactly how light works and exactly how we interpret it. So just to start off, light is interesting in part because we can describe it in these dual, seemingly conflicting ways. We can describe light as a particle, so photons with energies given here as capital E, and in astronomy we usually use energy in units of ergs. Or we can describe light as a wave, so having a wavelength of lambda, a frequency of nu, and that velocity c, the speed of light. We can connect all these terms using these two equations. So wavelength is just equal to light's velocity c divided by its frequency, and we can also stick these into terms of energy. So light's energy is equivalent to h, the Planck constant, times nu, or if you like thinking in wavelengths instead, h times c, the speed of light, over lambda, all in ergs. You can see how these two equations feed into one another, and it's a relationship that's pretty straightforward. The key thing to remember and kind of store in your brain from this math is that higher energy light corresponds to a higher frequency, which corresponds to a shorter wavelength. So if we go to a little schematic of the electromagnetic spectrum, you can see how this works. The labels here for how we describe light as we move from gamma ray to visible light down to radio also illustrate one of the themes that'll come up again and again over the course of this class. Astronomers like to play it a little fast and loose sometimes with units and with naming things. So we annoyingly don't standardize the terminology that we use when we talk about light. It varies depending on where we are in the E&M spectrum. In the middle of the spectrum, we speak in wavelengths. And the good news is that this is primarily what we will be talking about and using in this class. When we talk about visible light, we tend to put our wavelengths in units of angstroms. So 1 angstrom is equivalent to 10 to the minus 10 meters. And it gives us these nice manageable numbers. So in the visible, we have wavelengths going from about 4,000 to 7,000 angstroms. A little shorter wavelength in the UV, we tend to work in angstroms as well. And if we go to longer wavelengths into the IR, we still talk in wavelength. We often make our lives easier by switching from units of angstroms to units of microns. So a micron here is 10 to the minus 6 meters. If we go to higher energies, if we go to things like X-ray and gamma ray light, we switch from talking in terms of wavelength to talking in terms of energy. You'll hear gamma ray research described in terms of mega electron volt photons, in a couple really extreme cases, tera electron volt photons. Similarly, X-ray, we talk about kilo electron volts. On the other end of the spectrum, if you go down to the radio, we switch again, and you'll tend to hear light in the radio described in terms of frequency. So you'll hear a signal described as having so many hertz or megahertz or gigahertz or things like that. But the key thing that we'll be using for most of this class is the visible, so the light we see with our eyes. So we go from very short wavelength light, like the blue and violet, out to pretty long wavelength light in the red. So with this terminology established, we can go through a few basic properties of light that are worth remembering because they wind up being pretty valuable when we talk about the applications of light to astronomy. The first one is the inverse square law. So this is telling us that if you have a source with a given luminosity, L, its intensity, so basically how bright it looks, is going to be equivalent to L over 4 pi times r squared. So it's basically telling you that how bright a light source appears is dependent on the size of the area that you're spreading that light source over. This gets illustrated in a schematic like this, where if you move twice as far from your source of luminosity, the energy from that source is going to be spread over 4 times the area. So the intensity goes down to 1/4 of the original intensity. The easy at-home demo that you can do for this is if you grab a flashlight or a bike light or a flashlight app on your phone and point it at a wall. If you put the light source super close to the wall, it looks really bright. You see this bright, brilliant, concentrated sort of ball of light from whatever you're using. As you then back away from the wall, the light gets more diffuse, it gets dimmer, and you wind up with this much bigger but much fainter sort of illuminated circle. This winds up really important in astronomy because for some subtypes of stars and some types of supernovae, we actually know what their exact intrinsic luminosity should be. So we can combine how bright something should be with how bright it looks and use the inverse square law to figure out how far away it is. So if we've got something whose brightness we know exactly, we call it a standard candle. And using how bright something should be compared to how bright something is to measure distance becomes a really powerful way of measuring distances in the universe. So we'll come back to this more when we get into those types of stars and those types of supernovae, but it all comes back to this fundamental property of light, the inverse square law. So another key property of light is the angles that we see when we talk about reflection. The idea here is that the angle of incidence of a light ray bouncing off of a reflecting surface is equal to the angle of reflection when that light ray is then bounced off of the reflected surface. So theta sub I equals theta sub r. It's about the dullest equation that you can imagine, but I always like reminding people of this because it can feel counterintuitive when we're coming from the world of mechanics. I know that whenever I am building this in my head, I always want to make this angle a right angle. So there's this idea of, if I have a very small angle of incidence, I'll have a very big angle of reflection, and it's not in fact the case. The angle of incidence and the angle of reflection are always going to be the same. So small incidence gives you a small reflection angle, large gives you a larger one, and so on. We use reflecting surfaces a lot in telescopes, so understanding how these reflections work becomes really important when we start talking about telescope optics. Similarly, instead of reflection, we can now talk about refraction. So this tells us how a ray of light passes through a medium that has a different index of refraction than the air around it. So in this little illustration, the indices of refraction are given by the ends. So what we're saying is that light coming in through the air with an index of refraction of n1 will hit a piece of glass at an incident angle of I. So what we're saying here is that the index of refraction n1 times the sine of that incident angle will be equivalent to the index of refraction of the glass that the light is going into, n2, times the sine of r, the angle that the light is bent now that it's in the glass. This mostly becomes interesting because you can see what happens to light as it passes through a chunk of glass and then back out into the air. Because once it's transferred from that medium back to the air, the same principle applies and you go back to that original incidence angle. The effect here is that if you were looking at this light source on the lower left of the image from the upper right, you'd see a discrepancy between where the light appears to be after it's passed through the glass and been bent a little compared to where it actually is. Everything's off by some given distance. If any of you wear glasses like me, you can see this effect by just looking through your glasses and then dropping your glasses down your nose and then back up and seeing the difference. Another good example is if you've ever stood in a pond or the ocean and reached down into the water to grab a rock. If you reach down according to where the rock appears to you standing above the water, you'll miss it because the index of refraction of the water has slightly tweaked where you're going to think the rock is and where you're going to reach. This becomes important when we start talking about dispersion. So that index of refraction, so the change in the angle and how much the light gets bent when it goes from air into glass and then back out, is actually wavelength dependent. So this starts to get at how prisms work. If you shine white light into a prism, blue light with a shorter wavelength is going to be more bent than the red light with a longer wavelength. So that light is going to emerge out the other end of a prism, sorted into this nice visible spectrum because of the wavelength dependence of the index of refraction. So you can already see from this that a prism is a nice tool for potentially spreading out light. This can be really good in astronomy when we want to look at a parsed out spectrum of light, but it can be annoying for other reasons. Dispersion is the reason for something called chromatic aberration. So what you're seeing in this illustration is white light passing through a glass lens that's then bent and focusing that light. You can see that since the blue light is bent more than the red light, the blue light is focusing at one spot along the optical axis, so that black and red line through the middle of the screen, and the red light is focusing at a different point. So when you take these images together and try to focus an image from that lens to a single point and look at it, you get this sort of weird disco-y effect where the blue and red and different wavelength lights focus at different points. And if we were looking at this through a telescope, it would mean that the light would look blurry. This was actually a really interesting problem in early telescopes that used glass lenses, and we'll talk about how it got fixed in the next lecture. So the next principle of light that we want to touch on is diffraction. So here we're depicting light as a wave on the far left of this picture that's then passing through a little aperture, and we're describing that aperture, so that hole, is having a width of little d. You can see what happens to the wave after it's passed through that little hole. You wind up getting this weird ripple pattern as we look at the effects of the aperture on the wave nature of light. You can actually see lines of destructive interference. So there's sort of the bright central image of that light passing through the aperture, and then you can see these sort of dim, weird kind of, they almost look like an optical illusion, but they're not, patches where the light is very hard to see. I'm going to trace it with these red lines just to show you exactly what we're looking at. They land here and here. And those areas of destructive interference are splayed away from the main image by an angle of theta. So if we're putting theta in terms of radians, we can relate the width of that aperture, so little d, to the wavelength of the light. That angle between the bright main point of the image coming through this little aperture and the first point of destructive interference, that angle, theta, is equal to lambda over d. So just to help you picture what this would look like, if we were projecting this image onto a screen, this is what you'd see. You'd see the bright main image, and then you'd see those little fringes from destructive interference showing up as local minima. Right now, the way we're depicting it, we see the little minima above and below the peak of that main bright image. When we talk about apertures in astronomy, we're almost always talking about circular apertures, so the circle of a telescope. So if you imagine what this looks like for a circular aperture, if you kind of take this imagined screen that we're projecting this image onto and turn it sideways, like turn it out of the screen so you can look at it, you'll wind up seeing it look like this. So this is what you would see from a circular aperture. The bright main image is very visible as that bright point in the center, and then you see the effects of destructive interference, sort of the smaller sub-peak showing up as a ring around it, another ring of destructive interference, and so on. So this means that we now have a way to quantify the distance between things that we image through an aperture with a width of little d. And this is why this matters. This basic geometry is a function of the wavelength and the size of that aperture. So now try imagining looking at two light sources that are pretty close together. And that would look something like this new image that's appeared on the bottom. The diffraction rings from those other fringes outside the like first ring of destructive interference are interfering with each other. So now the image is starting to look a little weird, but you can still look at this and say, okay, there were two sources of light very clearly. Now, as we start pushing those sources of light closer together, the images start to merge and become less and less distinguishable. You can see now that the center of the right-hand image is actually sitting on the center of the left-hand image's second maximum. It's starting to look weird, it's starting to be hard to tell, but we can still resolve that there's two sources that we're looking at here. But if we go any closer, and if we put the centers of those two images over the local minima of the other image rather than the local maxima, like basically if we push them any closer together than the value of theta, we can no longer resolve that there's two sources. It just looks like a kind of weird, blurry single source. So because of this, we can use our definition of theta. We've taken the small angle approximation. We're saying that theta in radians is equal to the wavelength of light lambda over d, the size of the aperture. So with that, we can now define the resolution of this aperture. We want to express it in radians, so you'll see the resolution, it's sometimes written out as alpha, is equal to 206,265 arc seconds, basically how many arc seconds there are in a radian, all times lambda over d. And in this equation, you'll also see a little multiple of 1.22. That's basically just a numerical correction for diffraction from a circular aperture. You sometimes hear it called airy diffraction. So it's just a constant that we throw in to deal with the fact that we're talking about a circular hole that we're aiming light through. So you'll notice that it's wavelength dependent. So this means that if you've got a circular aperture, something like a telescope, the telescope's resolution is going to be different for red light versus blue light. But this still gives us a basic physical limit for how sharp a telescope image can possibly be. Now, the key thing to keep in mind here is where the size of the aperture is in the equation, so little d. You'll notice that little d is in the denominator of this equation. So with that in mind, consider this as just a quick question. A 10 centimeter telescope has a resolution of about 1 arc second at a wavelength of 5,000 angstroms. Going by this, the Keck 10 meter telescopes in Hawaii, so telescopes with 10 meter mirrors, each have a resolution of what? Think about it for a second. See if you can just remember what the relationship would be without going back to the equation. Take a second and then I'll highlight the answer. So the answer here is A. The resolution of the Keck telescopes is 0.01 arc seconds. Because if you look at the relationship between the size of an aperture, the diameter of a telescope mirror, and its resolution, you can see that it's an inverse relationship. The 10 meter telescopes are 100 times bigger, so their resolution is 100 times better. This tells us in theory how sharp an image from the Keck telescopes should be, but this is describing what's called diffraction-limited astronomy. It tells us that we're getting images at the telescope's resolution of alpha. We're limited only by the laws of physics and optics and light. This never happens from the ground because of something called atmospheric seeing. So seeing is the term that astronomers use for basically our atmosphere messing with us. We see little turbulent eddies and motion in our atmosphere that winds up effectively blurring the images that come down to the ground and get captured by our telescopes. So if we really want diffraction-limited astronomy, we can either use pretty advanced optic techniques that we'll talk about in a couple lectures, or we can just go to space. So if we launch something like Hubble, we've made it above our atmosphere and we're now doing work in diffraction-limited space. And we're just limited by the law of diffraction that we just described. So going from diffraction onward, we can actually use the wavelength dependence of the equation that we just built to look at kind of another funny feature of this technique of passing an incident plane wave through a little aperture. This whole illustration is for something called single slit diffraction. We can move from diffraction into interference if we add a second slit, and we now have two slits letting light through and watching the light interfere. So with two slits, we basically see different diffraction patterns imposed upon one another. So we get distributions of diffraction patterns within each peak that manifest as these little tightly spaced peaks and troughs of constructive and destructive interference. So you can see like the envelope of single slit interference sketched here as a dotted red line. But what we're seeing with these little sort of spikes are interference fringes. And this manifests in a really interesting way when you remember the wavelength dependence of diffraction. So this is a more in-depth question to think about a little bit. If the distance between two slits increases, so in this illustration, we have two slits, S1 and S2, separated by a distance A, and we're passing light through it to project onto a screen on the right-hand side. If the distance between those slits increases, the distance between the interference fringes is going to what? Is it going to increase as we put the slits further apart? Is it going to decrease as we move the slits further apart? Is it going to stay the same, or it doesn't matter, this is going to depend on wavelength, and I haven't told you the wavelength of the light yet? So think about it for a second. Try and imagine what it might look like if you moved the slits farther away and what that would do to the interference fringes of the light. And then we'll animate this illustration and look at the answer. So we're going to move on and animate the illustration, and you can now see what's happening. As we move the slits farther and farther apart, the fringes, the distance between the fringes starts to decrease. So this winds up coming out to this equation. Delta x, so the distance between fringes, is equal to the wavelength of the light times the distance, so how far away we actually are, how far we are from the slits to the image, and then this is all over A, so the distance between the slits. So you can see that wavelength is in here, but wavelength isn't going to change the fact that as you move the slits farther apart, the distance between the fringes is going to decrease. However, if we wind up, there we go, if we wind up doing the same thing with wavelength, if we change wavelength, that's now interesting to think about in terms of what this does to the interference fringes and how that appears. So this is sort of a spelled out and summarized version of the little animation that we just had on the last image, on the last slide. And now I want you to think about what happens if we change the wavelength. So if the light gets redder, if the wavelength gets longer, the distance between the fringes now is going to what? If we don't change the separation between the slits, if we don't change anything else, if we just make the light redder, the distance between the fringes will what? Increase, decrease, stay the same, or the answer depends on how far away the two slits are. So think about it, and then we'll animate and see what happens. So now we're going from red light, we're going from ultraviolet light to blue to green to yellow to red. The wavelengths are getting longer, and you can see the distance between the fringes now is increasing. So the distance between fringes increases as a function of wavelength. This is totally unsurprising if you have the equation in front of you and just try to balance it by doing the math, saying, all right, we're raising lambda, so we must be raising delta x. The reason this is interesting comes when we think about what this means for trying to build a spectrum. If we're sending white light waves through a whole bunch of slits, like if we go through a multi-slit setup, we'll see that light separated into orders, into those different little interference fringe bundles, and we'll see it separate out by wavelength. The red light gets splayed apart the most, the yellow light is splayed apart less, and the blue light is splayed apart the least. There's a cool example of this if you have a DVD or any kind of disc like that sitting somewhere in your house. If you grab it and look at it and kind of wave it around, you can see the rainbows that it makes of the white light in your room. And that is coming from the tiny little grooves on the back of the disc that wind up reflecting light and acting basically like these little interference fringes. So the white light coming in is going to bounce off to different degrees because of those tiny slits on the CD. This kind of phenomenon is known as a diffraction grating. So if you feed white light through a series of sort of grooves or slits like this, you'll see this sort of rainbow prism-like effect, but coming not from an actual prism, not from changes and wavelength dependence in the index of refraction, but from diffraction and the wavelength dependence of diffraction. So that winds up spitting out a spectrum. And this becomes an interesting question when you start thinking about something like telescope design. If you want to observe a spectrum of a star, you're gathering light from the star and then you want to pass it through something that spits out a rainbow, basically. And you might wonder, would you rather use a prism or would you rather use a diffraction grating like this to get something's spectrum? In reality, a lot of telescopes wind up using this phenomenon of a diffraction grating because you can machine a grating to give you the exact separation between those different slits that you want. And then as a result, you're able to very carefully control exactly how much you've spread out the spectrum, exactly how far you're sorting blue light from red light and so on. Prisms tend to give you less control. In practice, we sometimes use both. You'll hear about something called a grism, which is a combination of a diffraction grating and a prism. But it's worth keeping in mind when we think about wanting to separate light out into its spectrum and what that means for how we capture a spectrum with the telescope. So here's a recap slide of everything we just talked about. These are the basic properties of light that we stepped through one by one, and the key terminology or equations that we want to keep in mind as we talk about these relationships. So with this, we're now going to go on and dig into where we just kind of ended, which is making a spectrum, actually separating out light out according to its colors and what we can learn about different pieces of a spectrum. So we'll use this schematic as a sort of guide for talking about these details. So what we're imagining here is a hot light source, which is depicted near the middle of this image. And we're imagining observing that light source in 3 different places with 3 different prisms. To the left, we've got a prism that's just seeing the light source totally unobstructed. It is just staring at this light bulb or star or whatever light source we have and sorting the light out by wavelength. And that gives us what we would call a continuous spectrum. On the right, we've got 2 other prisms. In that case, we have the hot light source behind a thin cloud of cool gas. And we've got a prism staring at that light source directly from the other side of that thin cloud. So the light's passing through the cloud and then reaching the prism. And that winds up giving us something called an absorption line spectrum. So what we're seeing is that light source that has now experienced some absorption as it passes through that cloud. And the absorption line spectrum is telling us exactly what elements are in the cloud, exactly how much absorption they've caused, and we're getting something like a chemical fingerprint of that cloud. And then the final prism, the little pink one on the bottom, is looking not directly at the light source, but just at this thin cloud of cool gas that's getting heated by the light source passing through it. It's seeing kind of glowing emission lines from that thin cloud of gas because that gas is now getting heated. So there's atoms or molecules in that gas getting excited and emitting light that prism would detect. Since that prism isn't pointing right at the light source, it's not seeing any light from the light source itself, it's just seeing the effect of that light source on heating the gas. These 3 setups are analogies for what we see when we look at things in astronomy. The best analogy is probably the yellow prism on the right, because a hot light source passing through a thin cloud of cool gas is an excellent analogy for a hot star that we're observing, seeing light from the star passing through the star's outer atmosphere. So we want to break that down into 2 different components. We want to start by just looking at the continuous spectrum of the light source, and then later on we'll go back and look at what passing through a thin cloud of cool gas would do to that spectrum. So we'll start with the continuous spectrum and look at things like the shape of the spectrum and what we can pull out of it. We would call something like this continuum radiation, and we can approximate continuum radiation with a black body. So a black body is opaque. It radiates light distributed over different wavelengths as a function of its temperature. And And we're imagining here just a perfect black body that's emitting all of this energy evenly without any interference. You can describe the energy of a black body with the Planck function. Some of you may look at this and go, oh yeah, no, we just did that in thermo. Others may have never seen this before. That's fine. This is basically telling us that we can quantify the energy of a black body with this equation. And a key early takeaway here is that there's some energy being emitted at all wavelengths, even if the energy is exceptionally low. You can see the wavelength term popping up a couple times in this equation. This energy, by the way, is in a unit that we would describe as ergs per centimeter squared per second per angstrom. These seem like ridiculous units, but they're telling us how much energy we're emitting per square centimeter with every second that goes by at a given wavelength. So that's where that angstroms term comes in. So there's a big mess of terminology in here. You can see Planck's constant, you can see the speed of light. There's an exponential because that keeps things fun. But the term that we really want to pay attention to here is T. I can leave digging into this equation to your thermo class. T is what we care about here. T is the temperature of the black body, and we are connecting that to the energy emitted by the black body and the wavelengths where that energy is emitted. Everything else in this equation is a constant. So the thing that we're pointing to here, and that is the main takeaway when we talk about continuum radiation, is the shift in the peak wavelength as T changes. So now I want you to look at these sort of different black body radiation continua that are depicted on the plot. And you can see that at the bottom we have a solid line corresponding to black body radiation from something with the temperature of 3000 Kelvin. And you can see the shape of that radiation peaks right at this wavelength, so right around what, like 1.2 microns. As we depict black bodies with hotter and hotter temperatures, so 4,000 Kelvin, 5,000, 6,000, you can see that that peak, that point where we're at the wavelength where the most light is being emitted, is drifting to bluer and bluer wavelengths. So by the time we get up to a black body with a temperature of 6,000 Kelvin, that peak is now much shorter. That's now down at around 5,000 or 6,000 angstroms. So that shift is what we're interested in. And describing that shift mathematically is actually really easy, even from this mess of an equation, because what we're trying to find is the peak of the black body distribution, the point where the most light is being emitted and what wavelength that's happening at. So we can just take the first derivative of Planck's function and look for the point where the first derivative is set to 0. When you do this, what ultimately comes out is this relationship. So it's a relationship between the peak wavelength of a black body continuum and that black body's temperature. So it's 2.9 times 10 to the 7 divided by the temperature in Kelvin. The takeaway here is that as the temperature goes up, the wavelength gets shorter. So you can see that just by looking at the plot. As we go to hotter temperatures, the peak wavelength moves to shorter and shorter wavelengths and gets bluer. So this relation is known as Wien's law. Hotter means blue and cooler means red is the main takeaway from this. Whenever I give a public talk on astronomy and I talk about hot blue stars and cold red stars, someone always gets annoyed because they're used to seeing cold temperatures in their kitchen faucet or their shower shown by blue and hot temperatures shown by red, because we think of ice as blue and cold and fire as red and hot. It is a lie. All faucet labels you will ever see are a lie, and you're not going to forget this now, because black body radiation tells us that the hotter something is, the bluer its peak wavelength is going to be. So take another good look at the black body continua that we have on this plot, how their peak wavelength evolves with temperature, and how the overall shapes of these different black body continua relate to one another. And with that in mind, there's an in-depth question that I want you to think about. So you want to observe two stars that are identical in everything but temperature. They're the same distance away, they're the same size, they're the same brightness, everything. Star X is 60,000 Kelvin, so really hot. Star Y is 3,500 Kelvin, so very cold. You're doing these observations with an infrared telescope, so something that observes pretty long wavelengths. To collect the same total amount of photons from both stars, which of these stars should you observe for longer and why? Do you want to observe star X for longer because it's hotter and therefore it's dimmer in the infrared? Do you want to observe star Y for longer because it's colder and therefore dimmer in the infrared? Or does it totally not matter? The stars are the same size, we don't care. So think about this for a second, maybe rewind for a second, look back at the shapes and the relative energies emitted by those different continua, and then come back and we'll head on to the answer. So the answer here is that you would want to study star Y for longer. It's colder and therefore it's dimmer in the infrared. This is a question that professional astronomers will frequently get wrong because star Y's peak wavelength, the place where star Y is emitting most of its light, is going to be redder and farther to the infrared than star X's peak. But the whole continuum, star Y's entire continuum, is still dimmer than star X because star Y is colder, star Y is emitting less energy. We can see that when we go back to the plot and look over here at long wavelengths where we're well into the infrared. That 3000 Kelvin blackbody curve may have peaked at a longer wavelength than the 6000 Kelvin blackbody curve, but when we move out to this distance, you can still see the 6000 Kelvin curve is simply emitting more energy everywhere. It's just a function of the Planck function and the idea that something with a higher temperature is going to be emitting more energy. So with that in mind, we can kind of do the opposite bit of calculus to this equation that we talked about before. To get Wien's law, we took the first derivative, set it to 0, and found the peak of these curves. Now we want to think about integrating under the curves. So if we integrate over all wavelengths using the Planck function, we get the expression for the total energy emitted by this object. And that winds up boiling down to this, the Stefan-Boltzmann law. So it's nicely simple. Again, we just managed to grab a big pile of constants and break them down into a new constant, sigma, the Stefan-Boltzmann constant. And you can see that energy at all wavelengths is equivalent to sigma times t to the fourth. Since we're now doing this in all wavelengths, the units have changed a little. We've now got ergs per centimeter squared per second, but we're no longer talking in terms of per angstrom because we're talking about all wavelengths. And this relation, the Stefan-Boltzmann law, tells us how changes in temperature translate into changes in energy. So there's another in-depth question to consider when we're dealing with this. Energy equals sigma times t to the fourth gives us ergs per second per centimeter squared. So the ergs per second emitted by each square centimeter of a star. A star's luminosity, you'll see it written as L, is defined as the total ergs per second emitted by the entire star. So if we just assume that stars are spheres with some radius r, if we make a star colder, but we keep its luminosity the same, what does this mean? Does that mean the star is going to get denser? Is the star going to get bigger? Is it going to get smaller? Or is what I just described impossible? Is it impossible to keep a star's luminosity the same if you're cooling the star off? So think about this for a second and consider what it means mathematically when we're trying to relate the energy of a star given by sigma times t to the fourth to the luminosity, the total ergs per second emitted over the entire star. Grab a pencil and a piece of paper if you want, try and scribble out what this might mean and what this implies for what's happening to the star. Pause if you want to, and then we'll come back and look at the answer. So what I just described of luminosity, the total ergs per second emitted by an entire star with some radius r, you can write that out like this. When we're looking at a star, we're effectively seeing the surface area of a sphere contributing to the star's total luminosity, so how much ergs per second is coming out of the whole star. The surface area of a sphere, we can call that A, is 4 pi r squared. So the luminosity is just going to be energy times area. So our description for the luminosity of a star, L, is 4 pi r squared times sigma times t to the fourth. So with that equation in mind, you can now think about what you would need to do to a star to hold its luminosity constant if you dropped temperature. So if T goes down and L is staying constant, the only other variable we have to work with on the right side of the equation is R, and you'd have to raise it. So this means that if a star is cooling off, but its luminosity is staying the same, the star must be getting bigger, it must be inflating. We actually see stars do this all the time over the course of their evolution, and it's something we'll come back to later on when we talk about stellar evolution. So, this is now a nice summary of what we've gone through when we talk about continuum radiation from a star. We've gone through the Planck function describing the relationship between temperature and energy emitted by a black body. We've looked at the Stefan-Boltzmann law describing how much energy at all wavelengths something is going to emit as a function of temperature. We've derived this super handy equation for the luminosity of a spherical star with a radius r, and we'll come back to this again and again in the class. And we've talked about Wien's law, so this way to predict where the most light is going to be coming out of an object as a function of temperature. So if this was all that happened, astronomy would be super easy. We'd just take pictures of everything, we'd measure the color, and we'd be done. The kicker is that we're also contending with atoms. So this is why in this little equation, or in this little schematic, we aren't really ever dealing with the prism on the left-hand side of the screen, at least not alone. We're dealing with these kinds of observations. We're dealing with what a hot light source does to clouds of gas, like the atmospheres of stars, and how that manifests as a spectrum. So the last thing in this lecture is going to be looking at how to make a spectrum and what those lines in a spectrum tell us about what we're seeing. We know that lines in spectra can be approximated by the Bohr model of an atom. So I'll do a little fake helium atom. You can see my nice little keynote illustration of 2 protons and 2 neutrons in the core, and then 2 electrons hanging out at a particular energy level. Just to remind ourselves of how this model works. Remember that each element has a different number of protons, electrons, neutrons, and the energy levels therefore have different energies. You always see the energy levels just described as integer multiples, so energy level n equals 1 is going to have an energy of e sub 1, energy level 2 is going to have an energy of e sub 2, and so on. And remember that physics tells us that an electron always wants to sit at the lowest energy level possible, or have the lowest energy possible for a given gas temperature. So with that in mind, we consider what might happen to these electrons to change their mind and get them to shift to different energy levels. If we send a photon zooming in to strike this helium atom, and that photon hits one of the electrons in the atom, that photon is going to impart its energy into that electron. The electron is going to get very excited, it's going to absorb that photon, and it's going to hop to a higher energy level. So that electron has absorbed that photon. It's moved to a higher energy level as a result, but the photons exciting that electron have been taken out of the spectrum of light that's passing through this helium atom. So this means that we lose photons at a very specific wavelength, and we get this spectrum, where the wavelength of that little dip corresponds to the energy difference needed to excite the electron and the wavelength of the photon that managed that energy difference. So that's how you get an absorption line. Light will be absorbed by a photon coming in and exciting something like a helium atom. Now, once that electron gets a chance to, calm down, it will drop back to a lower energy level. And when it does that, it loses energy, and it loses energy by emitting a photon. So that, again, gives us a spectrum that looks like this. You'll see a continuum spectrum and then a small peak corresponding to the energy of that change because of the photon that the electrons emitted. So every transition in every atom has a specific energy, and as a result, it has a specific wavelength associated with it. It's just a question of whether the energy is being gained by the electron absorbing the light and jumping up an energy level, or whether it's being lost, so the electron emitting light and dropping down. So we can go through the math of how that change in energy translates to a numerical energy and eventually to a wavelength. we can start off by assuming that the electron is held in its little circular orbit by electrostatic attraction. I know this isn't quite perfect, but for the Bohr model of an atom, it's an excellent approximation, so we can stick with that here. And that gives us this equation. We can set m sub e, so the mass of the electron, times v squared, so the velocity of the electron in its orbit, over r, the size of that circular orbit. Basically, the centripetal force of that electron can be set equal to z, the atomic number of the atom, times k sub e, so that's Coulomb's constant in this case, times e squared, the charge of the electron, all over r squared. We're setting the centripetal force of the electron in its circular orbit relative to Coulomb's force. So yeah, the electron's held in that orbit by electrostatic attraction. If this doesn't look terribly familiar to you, don't worry about it too much. This is a walkthrough to get us from how electrons work to the energies that we're talking about and the wavelengths that we're talking about when we observe a spectrum. So we'll take that relationship and set it aside, and then just rearrange some terms to get an expression for that electron's velocity. So if we just reshuffle that equation, you wind up with this. The velocity is equal to the square root of all that business. With the velocity and the equation for kinetic energy, we can just say E equals 1/2 m sub e, the mass of the electron, times v squared, the electron's velocity, and determine the electron's total energy at any radius. So this winds up giving us an expression for the electron's energy at any given radius in the atom. We know that an electron isn't just going to hang out at any old radius because of the quantum rule. So we're not going to go into the derivation, we're not going to worry about the background of where the quantum rule comes from, but we can invoke this rule, which is stating that the angular momentum of an electron has to be an integer multiple of h bar. So h bar, remember, is just the reduced Planck constant. It's h divided by 2 pi. You can think of it as like a quantum or a unit of angular momentum. And this statement is telling us that the mass of an electron times v times r, its angular momentum, has to be an integer multiple of h bar. So that integer multiple in the equation, that n, is what we think of, remember, as the energy levels. So now we can grab that, substitute it into the expression for velocity, and if you do the algebra out, you wind up with an expression for the orbit radius of the electron as a function of n, this nice integer multiple that corresponds to energy levels. Then we can combine this with our expression for energy and get this with more algebra. This gives us the energy of the nth energy level for any atom, as determined by the atom's radius and the atom's atomic number. So there's a whole pile of constants in here. We don't care about those. We can reduce that to this number, 13.6 electron volts. So this term, this 13.6 electron volts, is the Rydberg energy. It's the Rydberg unit of energy. You'll sometimes hear people refer to things as having an energy of 3 Rydbergs or something like that. This detail, this 13.6 multiple, is a useful unit to think of. You'll see it come back in a second. But for now, let's just grab that Rydberg energy and tuck it over to the side. Taking the Rydberg energy and dividing by the Planck constant and the speed of light gives us the Rydberg constant, so just r here as opposed to r sub e. And we can then put the Rydberg constant into the Rydberg equation. I don't know what exactly Rydberg did to get 3 different things in the same concept named after him. It's a little bit annoying, but when in doubt, if you see an R, call it the Rydberg thing. So what this winds up meaning is that we now have, with the Rydberg equation and the Rydberg constant R, an expression for the wavelength of any transition happening in a hydrogen-like atom, so an atom that we can approximate with the Bohr model. So remember, R here is the Rydberg constant, capital Z here is the atomic number, and the little n's here are those integer multiples of angular momentum that we use to represent energy levels. So now we can use this equation, this relationship between the wavelength of a transition between 2 energy levels and the energy levels themselves, the Rydberg constant and the atomic number, and try to math out what the wavelength of a particular transition is going to be. We can do this using hydrogen as an example because that makes our life easy. We can just make that atomic number Z equal 1. And we can approximate what the Rydberg constant is. Let's say that the Rydberg constant is approximately equal to 0.001 1 over angstroms. It's not quite that, but it's pretty close, and this makes our math way easier. So we'll stick with this approximation for the moment. With that in mind, grab a pencil and piece of paper if you just want to try and scribble out an answer, and try to do this. Given the information that we've put on the left, the 2-to-1 transition of hydrogen, so an electron jumping from the second highest energy level to the lowest energy level, from level 2 to level 1, that transition is going to fall into which wavelength regime? Now, an important thing to keep in mind here when you look at the Rydberg equation on the left is look at the two integer multiples of angular momentum that we treat as energy levels. You'll notice that the lower energy level is always on the left. It's always 1 over the lower energy level squared minus 1 over the higher energy level squared. Because whether we're going from level 2 to level 1 or level 1 to level 2, we're talking about the same amount of energy. The question is just whether the energy is being absorbed or emitted. But the amount of energy doesn't matter, and you'll notice that arrangement also makes sure that the answer always comes out positive. So, the 2-to-1 transition of hydrogen. Plug those numbers in, plug in the atomic number of hydrogen, which is 1, plug in our approximation for the Rydberg constant, and then see what wavelength you get out. As you're doing this, I'm going to pop up our electromagnetic spectrum schematic to remind you which values correspond to roughly which wavelength regimes. So take a second to do this, pause the lecture if you want, and then we'll come back and we'll look at what the answer is. So we can work this out. Z is just equal to 1. That thing in parentheses, 1 over n sub 1 squared minus 1 over n sub 2 squared, comes out to 3/4, and R is 1 over 1,000. So lambda here comes out to 1,000 angstroms times 4/3, or about 1,333 angstroms. From our electromagnetic spectrum, we know that that's a pretty short wavelength, and that winds up corresponding to the ultraviolet regime. So the 2-to-1 transition of hydrogen would show up as either an absorption line or an emission line in the ultraviolet spectrum of a star or a galaxy or whatever you're studying. Now, in reality, we made a little bit of an approximation here. R is more like 0.00109678, and that means that instead of the numbers that we posed on the right, we're a little different. The final answer is going to be 1216 angstroms, but that's still in the UV, and that is actually a line of hydrogen known as the Lyman alpha line that we see very frequently in astronomy. So you can go through and do this math out for the 2-to-1 transitions, for all the transitions down to the first energy level, all the transitions down to the second energy level, and all the transitions down to the third. And what you wind up with are these series, which you may have seen before. The Lyman series down in the ultraviolet, the Balmer series, which you see in the visible, and the Paschen series, which you see in the IR. So these wind up very nicely mapping to the sort of different observational regimes that we work in astronomy. The ones that we'll be running into over and over again in class are the Balmer series. So these are actually standard enough and common enough that we just refer to them as H alpha, the 3-to-2 transition in the Balmer series, which is 6,563 angstroms, and then H beta, the 4-to-2 transition, and H gamma, the 5-to-2 transition. These keep going, but this winds up giving you a nice little sort of once-over look at the hydrogen lines that we tend to see very often in the optical that you'll wind up running into again and again. If, as you kind of spend time working with astronomical spectra and working in astronomy, these become wavelengths that wind up, I don't even want to say memorized, they just become ingrained after you've seen them a lot. You do not have to worry about memorizing them, but I wanted to introduce you to these lines now because you'll be seeing a lot of them. So the last thing that we'll be doing today is looking at the anatomy of a spectral line, sort of how we build spectral lines and then interpret them in data. So if you've got a stellar spectrum and you've just got bright, constant light, you've just sort of got the continuum, and then you've got absorption from a particular atom, you can look at a few key properties of that absorption and try to suss out from that what you're looking at. The key thing is going to be what we call the rest frame wavelength of that line. So it's basically telling you exactly how much energy an atom has absorbed, which we just did all the math out for. That wavelength is going to depend on the composition of the gas that light's passing through, because it's going to determine whether you're seeing light absorbed by a hydrogen atom or a helium atom or a calcium atom, and all of these will have different wavelengths and different energy transitions associated with them. It's also going to wind up depending a bit on the temperature of the gas, because the temperature of the gas determines the gas's energy, which determines which energy levels the electrons are occupying. There's also the strength or the flux of the line, so basically how much light is being taken away by that line as a whole. It tells you the number of electrons hanging out in the energy level associated with that transition, and that also tells you things about the composition of the gas, so how many atoms there are in that gas and how abundant those atoms are as a function of temperature. So the next detail is the width of that line. You'll notice that it has sort of this very characteristic U-like shape, and we want some way to quantify how much light is actually being taken away, so how wide that line actually is. We can think of this line as having a particular area, A. So if you just integrated over everything in that line, you'd get a description of the line's area. The best way to define the width of a line is by something called its equivalent width. We can measure the area of the line and then imagine the theoretical perfect rectangle that would go from the continuum, so the point where there's no absorption happening in the spectrum, all the way down to 0, that has the same wavelength. If you imagine that perfect little rectangle line and imagine a rectangle line with the same area as the actual line we're dealing with, the width of that rectangle is going to give us the value of the equivalent width of the line. This takes away any weird guessing of, are you measuring the width near the little narrow bottom of the line or the big wide top of the line, and it gives us a consistent way to describe a line's width. So if you look at the shape of the line, you can also see it breaking down into lines with a sort of core, the sort of main absorption period, and then lines with these little wings, sort of the end of the distribution moving out to the blue and to the red side of the line. So this is a neat description of the shape of a line, but we've kind of glossed over something here. Why? Why is a line shaped like this? We just did a whole thing on how transitions between two different energy levels have a energy, have a wavelength, and a single wavelength transition associated with them. So why aren't spectral lines just little Dirac functions? Why isn't there just a single plummeting point in a spectrum where light is absorbed at exactly one wavelength, corresponding exactly to an atomic transition? So that's the question I want to leave you with at the end of this lecture. The Bohr model of the atom predicts a super exact energy for a given transition. So given this fact, why aren't spectral lines shaped like perfect little rectangular, perfect little Dirac functions, just absorbing one wavelength? So I want you to think about reasons behind why this might not be right, and we'll come back to answering that at the start of the next lecture.